Hi, everybody. Welcome to the Cheating Speed of Light talk at the O3D Econ of 2021. Have you ever played multiplayer games like Quake and Call of Duty or, well, New World, and wondered if, with the person you're interacting with, just like they're in the same room with you, but they may be hundreds or thousands of miles away, and how does that work from a kind of a technological standpoint? Well, it just so happens that engineers that work on games are just kind of amazing and kind of a very special crowd. And while in reality nobody really managed to break the speed of light, a lot of them have figured out how to work around it. A little bit about myself. My name is Oleg Bezerudko. I live in the beautiful Pacific Northwest in Seattle, Washington. I worked for AWS now for 8 years, and for the past year and a couple of months I've been focusing on games from the product standpoint. I've played games for as long as I can remember. In fact, I can probably attribute my command of English language to playing games when I was a kid growing up in Ukraine. All right, enough about me. Today we're gonna discuss the challenge of making multiplayer games, the possible solutions that, or the approaches that game developers take to overcome these challenges, and then later I'm going to hand over to my colleague Carl Berg to walk you through specifics of what we've done with O3D. Let's start by just kind of setting the background. We all know that games are a very interactive form of media. People they shoot a thing, they expect it to get shot, they talk to people, they want to interact with other people. And in order to construct this interactive reality, typically, any typical game has kind of a notion of a level, the world, or a map. All of the objects that you see typically in the map or in the world are often entities. In O3D, everything, actually including the map itself, is an entity. In order to define the behaviors to these entities, what developers do is they add the various components. Here I'm showing a player as an entity, so you would be controlling a player. I'm showing only 2 components, but in reality, every entity may have dozens of components with different behaviors. What we see is that every entity, there's that giant chicken you saw in the previous slide, has the kind of a set of properties that help it define what kind of triggers they have and how it behaves in different scenarios. And as developers go through the world and they fill it up with different things, they create plenty of those entities and plenty of the components, defining the remote procedure calls or RPCs and those properties. And here's the challenge, is that multiplayer games are kind of unique because the biggest challenge is that they have to deal with long distances. Players generally, when they play games, they have very high expectations. They've played a lot of single-player games. They expect that, if they play with another character, they expect that interaction to be very smooth, seamless, and instantaneous. And if you have some sort of a failure, it can feel very unfun. And if you don't have a fun game, you don't have a good game. We just happen to live in this guy's reality. He put some very hard limits on the universe. One of those limits is the speed at which various objects can travel throughout. We already know that the speed of light is basically the fastest object or the thing that can travel. And so we've built internet based on fiber optic, which due to its refractive properties, due to its refractive properties, it can get us to approximately 2/3 of the speed of light. With we know that light is traveling at 300 million meters per second. It's approximately 185 or 186,000 miles a second. And so if we do some math, just to kind of make it real, if we have two players, one is, say, in Seattle, another one is in New York, and we try to calculate best possible latency between them using fiber optic cable, if they were connected literally directly to each other, it would be about 18 milliseconds. In reality, it's quite different. Your typical ping from any host in Seattle to any host in New York you're going to get is about 80 milliseconds, and that has not improved in over 25 years. If we start dealing with like some really long distances, like we'll take Sydney to Montreal, the ping is around 250 milliseconds. And don't get me wrong, it's amazing that we can transfer information at this speed across the world. But in reality, it hasn't improved in a very long time. And this guy's laughing. So in order to discuss how game developers have come up with solutions to this problem, let's kind of discuss a game. We have here a very simple example of a player who's stationary. The only action they can do is to shoot at a specific time. And there's a wall that is their target that's moving in front of them in two-dimensional space. So their main task is to just hit that target. In our game, we'll have a server on the top here in blue. And the server will be responsible for moving that wall. The client will be solely responsible for trying to hit that wall. The arrows that you see on your right, it's the network packets where the server is just sending to the client messages about the world update. As you can see here, the wall has shifted to the right. On the client, you can see that the wall is a little bit further, or it's lagging behind of where its location is on the server. That difference is practically your latency. If a player tries to shoot that wall, they will shoot it when they see it in front of them. But in reality, the wall is often, because of that latency, would have probably been already further down. So the client will send a message to the server, tell the server that I'm shooting, and the server, the wall has already moved on. The player might feel like they've hit the wall square in the center, but in reality they would have missed. So the world would tell them, or the game would tell them that they've missed. All of that is due to latency. So with this kind of scenario, there's 4 solutions that developers have come up with. One solution is do nothing, commonly known as build a dumb terminal. A dumb terminal is a terminal that only sends and receives messages from the server. It doesn't actually do any kind of computation locally. So in this scenario, if we approach this game with this dumb terminal approach, we'll have the server responsible for the moving of the wall. It will move the wall. It will notify the client. It will send that update. The wall will move on the client side. The player, once they see the wall in front of them, will click shoot, and they will shoot, and the wall is probably at that point has already moved on. They'll continue shooting, and they will miss the wall. This is dumb terminal. One thing to note here is the player will click shoot on the client side. It will send a message to the server. The server will then interpret the shooting action and will send that message back of the shoot back to the client. So then the client will have to play that. Because of this round trip latency, that experience can be very jarring. And here's an example of a famous game where a similar experience is, you can kind of see it. The player is trying to, they probably have a degraded networking or network conditions or something of that sort, or just low connectivity. They're clicking around trying to move their character, and it's just not responsive. After a while, the character starts moving. Developers are kind of tricky. They realize this, and so they add animations just to kind of provide feedback to the player that something is happening. They just need to be patient, but you can see in some cases, probably the network is really in a poor condition, and that just stops to be playable. Solution number 2, we can trust the client. In this case, we have the similar scenario. Server is moving the wall, notifying the client that the wall has moved. The client is waiting or the player is waiting for the wall to get in front of them. They shoot. They send a message to the server, I'm shooting. Once they shot the wall might have already moved on because of, again, set latency. But because we trust the client, the server will just say, yep, the wall is shot. You hit it. This may be a good approach, but in reality, it's very prone to cheating. And in a competitive environment, this is just not acceptable. So here's an example of a game where you can see on the top left, there's a handy cheater menu that the player is pulling up. And best I can tell, they're spawning other players that are on the map in front of them, only to shoot them immediately. The server fully trusts the client and registers those kills and obviously scores the game inappropriately, making a probably pretty bad experience for other players. So in O3D, we decided to just never trust the client. The third approach that you can take is predict the future on the client side. Here, same scenario as before. We have the server on the top moving the wall. The player is trying to hit it. The wall moves. The client is trying to figure out at what point the wall will be in front of me, so I can show it to the player based on their latency ahead of time and have them shoot it so that when I notify the server, it's actually in front of them. In this kind of a simple scenario, this will work. You can see on the sort of a left frame, if you will, the wall is moving towards the player, and then when the client decides that the wall is in front of them, it will notify the server that the wall was shot, and the server, it will look correct. But the problem begins is that we can't really predict everything always correctly. In scenarios where we have AI characters or other players, it's impossible for us to predict their movements always in every single case. So here, just for argument's sake, let's just say that that behavior of the wall bouncing off the edge of the screen and coming back only exists on the server and client is not aware of it. It will try to predict that the wall will continue moving left to right and then move off of the screen, ending up in a totally invalid state. So we're just not going to try to predict the future anymore. Here's an example of how that behavior manifests itself in an actual game. If you look not necessarily at the character itself, but the vehicle, I think, in the background, you can see it's very easy to see how it snaps back. That's in games, in the game culture, it's called rubber banding. The client is predicting that the vehicle and the character will kind of traverse through the world, but when it starts reconciling with the server, that in fact didn't happen, so it snaps them back. The fourth solution, that's the solution that we've gone with in O3D, is build a time machine. And as any good time traveler, we're just going to visit the past, we're not going to alter it. So here, what we do is, on the server side, we effectively keep a record of the world state. We have a column for time. It can be measured in any kind of units. And we're keeping track of the X and Y position of the wall. From time 0 to time 10, you can see that on X-axis, the wall has moved from 50 to 150 points. And as it keeps going, moving left to right, we keep record of it. And then at some point, of course, as we move the wall, we keep notifying the client. At some point, the client will decide to shoot the wall. And at that point, the client can echo back the timestamp at which it shot the wall. That message of I shot the wall at the time 20 is very meaningful for the server, because at that point, server can, even if it's moved on, it can rewind back and see what state the wall was in when the client had shot it. And they can confirm whether it was valid or not. Of course, you still shouldn't trust the client, so you'll probably put some kind of boundaries where you won't let the client tell you they shot the ball 5 minutes ago. So you probably track it within seconds or depending on your gameplay loop. That's kind of it. At this point, I'm going to hand over to my colleague, Carl Berg, to walk you through some more technical details of what we've done in O3D.
I'll mask. All right. We're good for the mic? OK. So I'm Carl Berg. I'm one of the principal engineers on Open3D Engine. And I'm just going to go through some of the more algorithmic details about what Oleg just described. So a little bit of pseudocode, and I'm going to try and tie it into like what we've done specifically inside the engine a bit. Just to start off, I want to define something we sort of call the input structure. And I put this delta time here. In practice, you never want to do this, because again, we just talked about client authority. And putting values in here that are not really like directly inputs. I'll describe inputs better in just a second. But putting something like a delta time there is actually really bad, but it makes the code really easy for me. What we do want to put are things like this, right? So you've got mice, you have keyboards, you have controllers, you have sticks, various buttons that you're interacting with. Those are the things we want to capture as inputs. And I'm not going to put like actual keys there, because we generally want to have some sort of action mapping in there so players can remap for their own custom preferences. But generally, these are the type of things we want to put there. So again, we don't want to do this, right? Where we have state that is computed as a result of those inputs. So like number of shots taken, that's something you compute as a result of whether or not you press the fire key. So putting that inside your input would be client authoritative, and would be very bad, because then they can tell you they've shot when they actually haven't. Instead, we're going to take all of that computed state, and we're going to move that into a different structure that I'm going to call the player state. And what this really defines is the set of, I'm going to call it predictive state for the player. So there's going to be a series of values that we're going to allow the client to locally predict, but the server is still going to have ultimate control or authority over. I'm also going to define a couple other structures here. So the first is going to be what the concept of the world state is. So for those of us from like an ID tech background, or like Quake, Doom type style, this will look very familiar, because they actually do this. They'll define a single big structure for the world. We don't quite do that in Open3D Engine. I'll talk about how we've deviated a little bit there. And I'm going to define a world state update packet. So again, that packet contains the full state of the world, as well as the timestamp that we need for the server to do its backward reconciliation. So that's our world state, and that's our packet. The other thing I want to define is a tick function. And games are very, very frame-based, right? So we iterate from one frame to the next. So this tick function, it's basically responsible for taking that player predictive state that I just described and moving that from one state to the next state. And this takes a triple of inputs. So it takes the predictive player state structure that we just defined. It takes the state of the world, and it also takes the input that we just defined as well. To actually take a look at what you might see inside the tick function for one of these guys, it looks generally something like this, right? So if like our move forward key is pressed, for example, we're going to Euler integrate our position by some amount. And you'll see like the delta time shows up there. That's why I put it into the input structure. It just makes this code work out really nicely. For Open3D Engine, actually, we use a fixed input rate. So instead of having like an explicitly defined time in our input packet, the concept of time is associated with the number of inputs that we process. And again, like that's implicitly client authoritative, because you can think of like a client hacking their local program to send maybe 100 times the input packets that they're supposed to send for a given second. So we still need guards around that. So we do something called bank time in Open3D Engine, which effectively keeps the client within a certain tolerance or window for the number of input packets that we receive for any one given second. And if they fall outside of that, we're going to take over and correct them. And again, if we've got our move backward key, we're going to Euler integrate backwards. It's not very interesting. And then, for example, if the fire key is pressed, for the really basic wall example that Oleg just presented, so if the fire key is pressed, I'm always going to increment the number of shots I've taken. And now we can just check the player's position against the wall state position from the world. And if that lines up properly, we can increment the number of times we've hit the wall. So in Open3D Engine, we store all of this world state, actually, and the predictive state as network properties on components. And there's going to be a lightning talk tomorrow that I believe is going to go into more details about how this works. So the world state, those are typically defined as rewindable network properties. I'll just call it that. And that allows the server to basically track that history of values. And then the predictive state, you mark them as actual predictively. And by marking those network properties as predictive, it allows us to basically write to those values on the client locally as we're doing input processing. The inputs are declared as network inputs on those multiplayer components. So you'll see in the Open3D multiplayer sample code, for example, there's going to be several components that declare network inputs, and that's where we're storing things like controller axes, button presses, mouse state. And again, for the rewindable state, we're not storing like an array of structures like we do in Quake or Doom. Instead, we're doing more of a structure of arrays. So we have individual network properties that have basically ring buffers of values that back them. And the reason we do this is because our world state updates are very delta compressed. So we may not get the full state of the world with every update. We're only going to get values that have changed. And the way we've done this is basically it's a very lazy system. So as updates from the world sort of come in on the client, we can basically say, okay, like, what's the most recent value we've seen, and basically backfill all of the values that haven't been updated with the last state that we had before, and then insert the new state we just received as an update at the head. And if you ever ask for a value that's outside of your buffer range, you can just return like the latest in your head, and it all stays consistent. It's accurate. So it's very low in our compute cost, and it allows us to scale these algorithms much higher than normally. The tick function that I just described, we actually split that into two in Open3D Engine. So it's a two-phase, create input that we run only on the client. And this is basically responsible for sampling your mouse state, your controllers, your keyboards, and writing it to those predictive network properties. Writing it to the network properties. And then we have another function called process input. And this guy is run on both the server and the client. And it contains exactly the code that I just described in the tick function. And that's responsible for basically incrementing the player's predictive state from one state to the next. Another thing to note is that we typically rate limit how often we send world state updates down to clients. Clients are playing at very different rates, potentially, right? We'll have players that are maybe at 60 hertz VSync, some that are 144 if they're at high refresh rate monitor. And we want all these players to have a very smooth experience. If we tried to have the server actually send world updates at 144 hertz to all of our players, we'd quickly saturate our bandwidth and not have a great experience. So that basically implies that at whatever rate we send inputs to the, world states to the player locally is going to have to interpolate extra states just to make things visually smooth for whatever they're playing at. And there's going to be other complicating factors here, like variable latency and like lost packets. They're going to make the rate at which we actually receive these world updates not consistent. And we still need to make sure things look very visually pleasing to the player. What we typically do is interpolate between the last state that we've received and the current state. In Open3D Engine, it's inside the multiplayer system component. We call it the tick visible network entities. And we actually compute a single global blend factor for every client. And the reason we do this is we want to be able to send that blend factor back up to the server because it's important that the server be able to reconstruct that blending we do in the client during its backward reconciliation phase. And if you think about it, this is because a player is shooting at things that are moving at very high frequency. It's very smooth on their screen. The actual network states that we've sent to the player are very quantized temporally. And if you shoot at one of those in-between blended factors, and the server doesn't do that same blend reconstruction, we're gonna basically do that same sort of missing behavior. So in order to get the like the high fidelity hit detection that we expect, we need to reconstruct that blend factor very accurately on the server as well. Here's a really simple example. So this is the multiplayer sample, which is not too fancy yet. We're still adding functionality here. But basically, I can walk around and I can run into boxes and shoot things and stuff. So you're going to see I'm rocking into boxes here. This is the view from the client screen. And those boxes are completely moved by the server. There's no logic on the client to actually move those boxes around. I'm going to basically add about a second of latency here and just repeat the same action. So now I'm moving around. You can't really tell, but on my client, everything is completely responsive still. So as I move the mouse and press my WASD keys, the player is responding instantly. It still feels like there's 0 milliseconds of lag here, despite there being a whole second of lag. But the boxes, because those are server controlled, those are actually lagging behind my motion by about a second now. And if I restore my input latency back down to 0 milliseconds, then you see everything becomes responsive again. So we've defined this process of locally predicting player state, but as anyone in the industry kind of understands, like making a fully deterministic simulation like this is really difficult, and all sorts of stuff goes wrong. So at some point, for a very large and complicated game, it's going to be impossible to make everything fully deterministic all the time. So we want some sort of safety guard in there that's going to basically return us to synchronized state if we do desync from what the server's processing. So here's a really simple example using that same wall game of what happens if we do something that desyncs. So in this case, I've got a client. It's going to process 3 inputs here. And you'll notice I've added this concept of a client input ID. That client input ID is effectively each client's concept of time for their locally predictive player. And that'll become more clear when I show another video. But effectively, like every player has a different view of the world. And that's separate and distinct from like the time that's being presented from the servers down to the clients. So we're dealing with multiple streams of time here, effectively. And this concept allows us to basically track the concept of time for each client independently. So I'm going to pretend that for whatever reason, the server's lost the second input packet. So in the first input packet, we didn't shoot. So if you didn't shoot, then you are not going to increment the number of shots that you've taken, and you can't have hit the wall. On the second input, our player did press the shoot button, so we incremented the number of shots taken, and we hit the wall predictably, right? So our state there is 1-1. On the server, because we didn't receive that second input packet, though, we don't have that state that the player said they hit the fire button. So the best thing the server can really do is just guess. At some point, it's going to realize, hey, I don't actually have an input for client input ID 2. It's going to have to do something. So it's going to backfill basically and say like, okay, I'm just going to assume the player hasn't changed their input state from whatever they sent me last time. So it's going to move forward and say, okay, I'm going to just generate my own client input for client input 2. They're not shooting and they didn't hit anything, right? So now immediately the predictive state we have in our client and the authoritative state that we have on the server, those don't match. We've desynced. And again, like as we keep processing inputs predictively on the client, we're going to compound this error. So the client on input 3 says, yeah, I did shoot, but the wall's moved on, so I missed. The server's going to get that and say, okay, yeah, you did shoot, so I'm going to increment the number of shots taken, but like I'm only at 1 shot taken now because I missed input 2 and I've never hit the wall. So now we have 2 outstanding states between the client and the server that we need to correct. So I'm going to add this little function here to my player's predictive state. I'm going to call it compute hash. The only responsibility of this is really just to sort of like walk through all those values in our player's predictive state and generate some kind of a fingerprint or a hash of what that state is. And it really condenses down like that whole player predictive state structure into like a very network-friendly fingerprint. To actually deal with corrections, though, is actually kind of easy. So on the client side, we're going to look at what our main loop is, basically. So for the client, like every frame, we're going to be calling this update method. And the first thing it's going to do is basically sample all of our inputs, so our keyboard and our mouse, by calling this create input function I just described. And it's just going to store off that input field that we just sampled. Then we're going to call the process input function, so that tick function. And we're going to pass in just our local client's copy of our predicted player state. We're going to pass in the input that we just created, and we're going to pass in the world state. So this is the last state of the world, the latest one that we've just received from the server. Now down here, this is where that hash function comes in, and this whole block here deals with basically sending stuff up to the server for us to properly reconcile. So we're going to increment this concept of a client input ID because we've sampled and processed a new input. We need to increment our concept of time for this input. I'm going to create that hash value by calling that predictive state hash function, and now I'm going to call the server and send an RPC to it. And I need to send 4 inputs here, right? So the actual input field itself, I'm going to send that up, the timestamp associated with that input, the last time that the world state was updated, basically. So I'm going to send that timestamp back that the server sent us saying, like, hey, here's the state of the world, and it's at time 5, right? I need to echo that back to the server so the server knows this input was executed against the world state at that time. And then the hash that we just computed as well. On the server, so we've got some little bookkeeping up there. That's just to make sure we're guarded against out of order or duplicate input packets. It's not very interesting, but the part that is interesting is down where we start talking about fetching the world state. So again, this is like a very Quake style approach. We're just going to assume we've got this array of structures of world state. So because the client input packet contains this timestamp, I can just go into that structure and say, like, okay, what was the state of the world at that time, and fetch that up back out. Now I'm going to call that exact same process input function, the tick function, and I'm going to pass in the arguments. So the player's server authoritative state, that same predictive player structure, but on the server now. The input packet that we just received from the RPC, so that's all the inputs, the fires and the move around presses and such. And then the world state that we just looked up, so that's the backward reconciliated world state, so that's the world state in the past. All 3 of those inputs, they should match exactly what was actually passed into that function, that same function on the client now at this point, but we're going to pretend we've done something wrong. So the last thing we do here is we're going to call that same compute hash function on that player state, and we're going to compute the server's authoritative fingerprint, basically, for the player's predictive state. And now if that server's hash doesn't match the hash that the client sent us with the input packet, we know that we've desynced, and we're going to send a correction. What that actually entails is actually not too much. So we're basically going to walk all of that player predictive state again, and we're going to serialize all of that up into one big correction packet and just fire that off to the client. And all the client basically does is just clobbers its state. So it's just going to overwrite all of its predictive state with what the server just sent it, right? So we're going to go back here. The server's going to send a correction packet for that input ID 2. We're just going to wipe everything clean and just write in the state for 2 that the server just sent us. So now we're exactly matched because we've just like raw copied all the data from the server over to the client. But we still have this outstanding input 3, right? And the client locally predicted that on their screen. So we've basically lost time, right? So like that concept of local client input processing, we need to restore that because you can't lose that input on our local predictive state. So we're going to start reprocessing that outstanding input, and there's just one input here in this example, but there could really be like dozens if we've got a really high input rate and high latency. So we were going to locally predict that we did take that 3rd shot and we missed the wall, and now everything's back in state, everything's reconciled. So here's an example of corrections in action. I think this is Anthem, I guess, but we've got a player here who's flying around, it's moving quite quickly, and this is sort of classic correction behavior. And I like this one because it's got these sort of particle trails off the sides there, so it makes the correction quite obvious. You'll see whenever the player starts snapping back. And for the blending that I just mentioned, like this correction is of such severe magnitude that it's actually overwhelming that blending. Normally we'll try and hide a correction like this so you don't even notice, but it's not really possible in this example. There's another really interesting thing that's worth noting here, and that's like for most of these games, we really hard lock the camera to the player, right? There's usually a fixed distance between the camera and the player. So when we do a correction like this, it's not just the player that's snapping. If you pay attention to the world around the player, that's also snapping as well. And because the distance here, it's not too extreme, but for stuff that's really close to the player, like really if you're against walls or other geo, that can move quite jarringly. And that process of like snapping the world around you, for many players, that could be quite nauseating, in fact. So there's a few things to note here. Like, corrections are expensive on bandwidth. Like that player predictive state structure can get quite large. So we don't want to transmit that unless we really have to. The process of actually applying a correction, so basically going back and reapplying all those locally predicted inputs instantly like that, that's also compute expensive on the client. So it can take up a lot of CPU time. And lastly, like this can be a nauseating experience for players if the correction is of severe magnitude. So despite the fact that we have this whole correction system in there, if you write gameplay logic that is desyncing frequently due to bugs or whatever, whatever source, don't rely on the correction system to keep your game in good synchronization. Like actually do the work, dig in, find out why it's desyncing, and correct that desync, because this is not a great experience for players. We don't want to do this. So everything that I've just described, all of the input processing, all of the input sampling, all of the correction behaviors, desync detection, 100% of that, that's all written for you. Everything's handled in Open3D Engine, so you don't need to write any of this code. It's all inside this single component, the local prediction player input component, which is kind of a mouthful, but it exactly describes what it does. And actually, that's the URL directly to the component inside GitHub, if you're interested. So if you crack that open, you'd actually see, here's all my client logic for local input processing, for local prediction. Here's all my server logic. Here's everything to deal with corrections. It's all right there. OK, so it's worth noting that we can't actually really cheat the speed of light here. Like those limits are hard, right? So even though we've created this sort of like paradoxical illusion that there's zero latency between all of our players, something has to give in effect, because we can't actually transmit information faster than the speed of light. So humans are actually pretty bad at dealing with these sort of perceptual inconsistencies. Here's an example. It's a very classic one. So I'm out behind this dumpster or crate. I'm shooting at something, and then I'll duck down, and then quite some time after I've obviously ducked down and I'm behind cover here, somebody is shooting at me and I die. And this can be really frustrating for players. This is like classic shot behind cover behavior. But there is actually some nice properties about this that I'll describe, despite it looking terrible. For the most part, usually, for the player who's actually performing the action, they're quite invested in the outcome of that action, right? So the player, when he's shooting, he's looking down, the iron sights of his gun, and he's pressing, the shoot key, and he's looking at what he's doing, right? Like your situational awareness of your own action is very high. And so if you shoot at something and you think you hit it locally on your screen, and then later on you discover the server didn't honor that, that can be really frustrating. That's something that players get quite upset about. For the player who's being hit, though, you don't necessarily have that same situational awareness. Like this is sort of an extreme example because the person's directly in front of you. But you could be getting shot from behind, or you could be getting shot from the side. You may not even know that the shooter is, on your, can shoot you. So when we want to bias here, we definitely want to bias towards the person performing the action. Like that sort of maximizes the benefit we get out of, people's investment into the game. So these algorithms, they do naturally basically bias towards the shooter, and that's a really good compromise for us. The other thing to note here is that I didn't put any time scale on those examples. So you'll note like there's no units here. Those could be like 0 seconds, it could be 10 milliseconds, it could be 20 years, right? Like there's no scale on that. And if you think about it, that's because the algorithms themselves don't really care, right? Like if you wanted to play a game with 1 year of lag, you could do that. All it would cost you is the memory to store all of that predictive, all the world state. And the algorithms are totally durable for that. It'll properly reconcile. But while the algorithms are durable, human perception here is not, right? Like if you played a game with 1 year of lag, it would be pretty boring because nobody else would move. And the server would reconcile everything perfectly. It's just like nothing would move on your screen while you're playing the game. So here is an example of like those multiple time streams. So again, this is the same multiplayer sample demo. And in the bottom left there, I have a player that I'm moving around, and the top right is just observing. And I'm walking into these boxes. And I'm going to do the same thing where I add about a second of latency to my connection. And I'm going to start repeating this, sort of like walking into the boxes. And as you observe on the bottom left, as I walk into the boxes, my player is responsive, but the world update to me is lagged out by about a second. But now you look at the player on the top right who's observing, everything is perfectly synchronized. He's basically got like just a couple milliseconds of latency to the server. So even though the bottom left has got a second of latency, the player and the boxes are still being received to me by those world states synchronously. So like everything looks really nice. And this, I like this because this really brings to point the fact that like every player has a unique perspective. The configuration of all the entities on all their screens is different, right? And it's the job of our server to be able to accurately reconstruct any of these visuals, right? So the server can equally reconstruct what's happening on the top right as it can on the bottom left. And for every player in the game, the server is capable of reconstructing this entity configuration. That's the point of the algorithms. So at some point, we're going to want to predict other things besides just like our local player. So it's really cool that we've got everything that you're directly controlling locally predicted, but it's kind of nice to be able to predict more than just that, because the more we can predict, you'll find it helps increase the immersion factor for the player playing the game. So a lot of stuff is actually quite easy, right? Like if you wanted other players in your game to flinch predictively when you shoot them or hit them, if you want other things like explosions or footsteps or decals, bullet holes, whatever, like all that stuff, it doesn't really affect your network simulation, so you can just go wild and locally do that in your client as much as you want. Even minor destruction, for example, like cups or stuff that's lying around in your world, you can destroy it. That's fine because it doesn't really obstruct the network simulation itself. Here's a really nice example that I like. So this is the foliage system in Cry 3, I think. And you'll note, like when you walk into it, it pushes the foliage out of the way. It's called touch bend. And stuff like this is fantastic because you can fill the world with these objects. They don't really obstruct weapons fire or other actions that you perform in the game, but it feels interactive. Like it feels the world is like interacting with your player. So even if you had massive amounts of latency, if all your foliage is touch bending as you walked around predictively, it'll feel like very immersive. It'll feel like you have a very direct connection to the world. So touch bending is a fantastic feature for this. However, at some point you're going to decide, I want to predict something that does affect the network simulation. The best example I can really think of is like the big rockets that you typically have in some of these games. So you shoot off a rocket. You want to, as soon as you press that fire the rocket key, you want to see that rocket spawn. You don't want to wait like 250 milliseconds or something for that rocket to suddenly show up. So you're going to spawn it right away, and you want to see that thing moving forward. But you also want other players to be able to dodge these things, potentially, right? Because they're slow moving, they deal very high damage. So we don't want that rocket to move with the player inputs like we did with the actual player itself. Because were we to move the rocket with the player inputs, it would do the same sort of shot behind cover behavior that I just mentioned. So a player that was trying to move out of the way, that could reconcile the player back into the path of the rocket and you would get hit, even though you thought you dodged it. So that's no good. So you want to locally predict the rocket. And if you actually think about this, when you send that fire rocket command up to the server, that whole time you're going to be locally predicting that rocket forward in time on your client. And you're finally going to get a message back from the server that's going to say, hey, like this rocket's been shot. We want where the server to say the rocket was shot. So the position that rocket should be, that should exactly line up to where the client's local prediction is at that point in time. So if you walk that through, that's adding round trip time milliseconds to the rocket's lifetime. We basically need to predict it forward into the future that far to get everything back into sync. So, if a player is shooting the rocket and you predictively shoot the rocket into some guy's face like this, this is the predictive result that we have, right? So like the player shoots, it's going to predict that thing forward by round trip time milliseconds. It's going to hit something on my screen. I'm going to see a big explosion, and then later we want the server to come back and say, okay, like the thing you hit really got exploded. We don't want this to happen, right? So you don't want to predictively shoot the thing, and then you get the server update, and finally, like suddenly the rocket just pops back into existence behind the thing that you shot. That would be very frustrating. So if you think this through, the only way to really properly reconcile this is when you get that message on the server saying you shot a rocket, you need to simulate the entire world from the timestamp where the player input was all the way forward to the very latest timestamp on the server, like immediately. And there's some tricks to do this very efficiently because that can be quite computationally expensive to simulate that many frames. But the scope of those algorithms are a little bit beyond this particular talk. but it is doable. So there's a few takeaways that I wanted to have here. The first is that it's very easy to solve very hard problems by adding latency. Latency is a really powerful abstraction. You can think of TCP making reliable ordered input streams, for example. That makes the networking really simple. And similarly, there's all sorts of problems we can solve by adding latency. But as soon as you spend latency like this, you can never really get it back. And again, because human perception here is not very durable to large latency values, the more you spend this latency as a currency, you can think of it, the worse you're making your customer experience. So spend it very wisely. Don't use it unless you really have to. The other is speed of light is a pretty hard fundamental limit. And you can imagine those first multiplayer programmers, those guys were incredibly smart, looking at the problem and saying this is impossible, how are we going to solve this? But in actual fact, they found a very elegant solution for it. And the algorithms that I presented are not particularly difficult, right? They found very elegant ways to solve it that actually maintain the benefit all the way around. So there's still full server authority. You still have very responsive controls. So the nice takeaway here is that even though it might seem impossible to solve a problem, there's ways to cheat, especially in games, that might solve the problem very elegantly for you. So don't get discouraged. And that's it for this particular talk. Thank you, guys.